Good morning. Um, this video will be on nanomaterials. Before I jump over to the notes, which are already posted, a few administrative details. This will be the last lecture for the quarter. On Friday, we will have a Teams question and answer. Um, for those of you who wish to take advantage of that opportunity, you can ask anything. Homework questions, um, or questions related to the material, things that come up from your review of the final review sheet, or just any topics that didn't make sense um, throughout the quarter, or at least the second half of the quarter. Again, this final exam is not comprehensive. It will just be on the second half of the quarter. The microfabrications, due to the fact that this class is essentially half one thing and half another, kind of with two half final exams. The homework solutions I've posted for both homework 5 and homework 6 on Teams. I have not yet finished grading homework 6, but if you want to review the solutions prior to receiving um, the graded your graded homework, that's up there for you to do that if you'd like. I hope to have that back to you either today or tomorrow. For the midterm, it will be very similar to what we did, or the final will be very similar to the midterm. Posted next week on the day of our assigned final. I still have to look that up. And you guys can take it at your convenience and just turn it into me for grading. And then that will put this quarter in the books. So I'm going to go ahead and set things up to talk about nanomaterials. And so these notes are not from our text. I built these based upon another book that was focused on nanomaterials. It was text that's not in my personal library. I had gotten it from the AFIT library. And since I'm not at AFIT, I can't just walk down the hall and get it. So I've not had a chance to review this text, and so these notes, luckily, stand alone fairly well. But the idea, the goal here is to highlight how what we have learned up to this point changes a little bit when we reduce our size regime another few orders of magnitude to nanoscale. So we've kind of been in the micro scale. With the first half of the quarter, we were talking a lot about how microstructure affects properties of materials, and then in the second half, we were talking about microelectronic fabrication, so and the micron scale. So if we go down another few orders of magnitude, we're talking about fractions of a micron. Say 100 nanometers or so, right? A tenth of a micron, kind of what we kind of, not a hard stop, but a generally accepted kind of what do we mean when we say nanoscale, so like 100 nanometers or so. Not quite atomic scale, right? That would be in the angstroms, right, or hundreds of picometers, right? So we're kind of in between the atomic scale and the micro scale, so you can't really see it unless you have the right instrument. Not optically can you see it, so that's kind of the scale that we're operating in. And the scale of feature, right, is going to dictate the properties and the physics involved. So, at the atomic level, right, the major interaction is particles, quantum mechanics, um, electrostatic attraction, those sorts of things. At the micron scale, right, we're talking about um, larger particles. So we're looking at van der Waals forces and electrostatic attraction still. But at the nanoscale, right, you have an in between here where yes, you have quantum mechanics coming into effect, but you also have surface area effects, volume versus surface area versus volume effects. You have still atomic bonding is important, right? So it is kind of this in between, and so I thought it helpful to spend at least a class period talking about some of those, especially since nanomaterial, nanostructure, nanoparticles, right, are becoming more common in material science. So to have what we call nanomaterials, so obviously, there are natural materials, we'll talk about some of them, that have nanoscale features. But we don't really talk about nanomaterials as them being nanomaterials, even though they have nanoscale features, because we don't really, you don't call them and think of them as nanomaterials until you have some way of controlling the size and the shape of those nanometer scale features, right? So obviously, natural materials have micron scale features, but we don't really talk about microstructure or its connection to material properties unless we have some control over what microstructure is forming, right? Via, say, heat treatments, mostly what we talked about. And so we don't really have a nanomaterial unless we have control over those nanometer scale features. So since nanomaterials are kind of at this crossroads, or getting to the realm where quantum mechanics starts to become important, or to the size scale where it becomes important, let's review a couple of things, right, about quantum mechanics. The first is that light and particles have a dual nature. We think of mostly, especially when we were talking about photolithography, light as having a wavelength. And so when we had diffraction, that wavelength resulted in constructive and destructive interference that gave us our diffraction pattern that limits the resolution we can get as a function of wavelength. And so light we most often think of as being a wave. But we also, light has a particle nature in the fact that we have a photon, we have a quanta of light that has a certain energy, and that energy is proportional to its frequency, or inversely proportional to its wavelength. So as the frequency goes up, a photon has more energy, and its related energy and frequency are related via a constant, we call Planck's constant. So a photon of energy, a quantum of light, right, is a photon, and its energy is defined by this relation here. And so when we think about some effects, say the photoelectric effect, where light absorption by materials has a quantum nature, we take advantage of the energy in a photon. And this also has implications when we talk about the absorption of light. So light is absorbed in discrete intervals, right? So one photon at a time, which if we jump down here and talk about the band structure, right, when we have absorption of light by semiconductors or emission of light, we deal with this quantum nature because the energy in a single photon, right, is going to match the difference in energy, say between one energy level in the valence band and the convection band. And this dictates the absorption properties of our semiconductors, or also of our nanostructured elements, which we'll talk about. By the same token, electrons also have a duality, except it's kind of reversed in that we think of electrons primarily as being particles, and we can manipulate them as particles. They have mass, they have momentum, they have charge. So when we talk about, we've talked about scanning electron microscopes or electron guns or electron beams, or plasmas. So we were able to separate ions and electrons on their basis of their charge to mass ratio and those sorts of things. And so we oftentimes think of them as being particles, but they also have a wavelength, just like light is wavelength and also has particle nature. Particles also have a wavelength, and it's defined by this relation here. Again, Planck's constant comes up again, except here it's inversely proportional not to wavelength, but to momentum. So that the momentum and thus the velocity of a particle dictates its wavelength. And so if you see here, it's inversely proportional to momentum. So the wavelength of an electron gets smaller as the momentum and the velocity increase. And we've talked about this in the scanning electron microscope and in the transmission electron microscope, that if you accelerate electrons to a high enough velocity, then their wavelength continues to get smaller, and this is put to great use to image at a higher resolution because we have a lower wavelength than you can achieve with optics. Okay, so sometimes we take advantage of the wavelength nature of electrons and particles also. But this dual nature is pretty central to the quantum mechanics of these photons and particles, electrons. So the simplest problem that you solve in a quantum mechanics course, right, is electrons in infinite 1D well. When you say well, technically what we're talking about is a region of low potential, right? So your electron here is at a low potential, but this is essentially energy. So it's in this well, and it needs to have a certain amount of energy to get out. Well, if the walls are infinite, right, it's never going to have enough energy to get out. And so classically, you would say this particle is stuck in this well, and it's never going to get out. But so back up a bit. So in quantum mechanics, the basic procedure, right, is that Schrodinger's equation is kind of a priori equation that relates the wave function, which is describing the particle, to its energy. And you get that by, and you solve Schrodinger's equation based upon some derivatives and second derivatives and the potential function. So input into Schrodinger's equation, very central input, is the nature of the potential that your particle or your electron is subject to. So in this particular simple example, that potential would be 0 in this region between 0 and A, and infinite everywhere else. And if you put that potential into Schrodinger's equation, and you take the derivative of it, and you impose the boundary conditions that the potential in this region must equal the potential at this region at the boundary, and also the derivative of the potential, and all those sorts of things, you get out a certain set of solutions. Now, those solutions for this particular potential here, this infinite potential well, look like this, right? You get wave functions that have this form. It has a sine function, and there's an integer in there which relates. So that, there's different solutions for different values of that integer. And if you plot these functions, it looks something like this, where you have these standing waves that form at different energy levels within the square well. So you get a set of solutions and a set of energy levels that dictate the solution to electrons in this potential well. And this will come into play later when we talk about semiconductor lasers and quantum effects. So that gives you discrete energy levels within this potential well. if I were to solve Schrodinger's equation, and we've talked about this when we talk about generation of the periodic table, especially in materials 560, if I put in the central potential, meaning the Coulombic attraction between an electron and a photon, or an electron and a proton, say in a hydrogen atom, right? I have a positive and a negative charge. They have a Coulombic attraction, right? That is my potential, not this infinite square well. So I have a spherical coordinate system. So I have r, theta, and phi, and I solve Schrodinger's equation with that potential, right? So I take the same derivatives that I had before, and I look for the set of solutions, and it's a much more complex solution, but I get out a set of solutions that are dependent upon a set of quantum numbers, right? And so the energy electron orbitals that we have in our atoms and the way that the periodic table is structured, right, comes directly from solving Schrodinger's equation for that central potential problem, which gives us our atomic structure. So you take that that arrangement of electrons in those different energy levels at different and there's different energy or electron orbitals at different energy levels, and out of that comes the atomic bonding. So there are certain energy orbitals that are almost filled, or just barely filled, or not filled at all, and that drives elements to bond in a certain way to get as close as they can to having a full complement of electrons. So in ionic bonding, that looks like ionic electron transfer from electropositive atoms that don't really want their extra electron to electronegative atoms that really want an extra electron in order to satisfy their valence. In order to have a full electron shell for their outermost electron shell. Or there are atoms that actually are halfway in between, right? And so they team up and share their electrons more or less equally and form covalent bonds, or electron sharing. Or you have atoms that have just one or two valence electrons, and they don't hold it very tightly, and they let it go, and they all share those valence electrons equally, and they flow around the crystal, right? So we get metallic bonds. Or you have elements that already have a full electron shell, like the noble gases, and they don't bond at all to each other, or only very weakly, due to instantaneous dipoles that form from the probabilistic nature of the electron distribution, right? Also known as van der Waals forces. And so that would be bonds between individual atoms. If you get together a great many number of atoms, right, you can form a crystalline structure. We saw this with single crystal silicon. And for the electrical properties of single crystals, or we care about the band structure. So there are in the band structure, the energy band structure is what you get when you have discrete energy levels of certain atoms, and then you put many of those atoms in close proximity. So I'm going to have the same electrons in each atom, but if they're close enough where those orbitals will start to overlap, then they're going to split those energy levels, and I'm going to get a continuum, essentially, of energy levels that we call band. And of course, you can make transitions from filled energy levels to empty energy levels, and generally we think of the valence band as being filled and the conduction band as being emptied, and so the name of the game with semiconductor physics is to understand how the band structure is structured. What are these energy differences between these various energy bands, and that allows you to design detectors where you're absorbing and creating free carriers, or light emitters where you are stimulating emission from filled conduction band energy levels to empty valence band energy levels, right, to give off light. Okay, so a lot of that should be somewhat familiar. Review. Sorry, just got a little bit condensed here. Did a little more talking, a little less pointing at various figures because it's a little bit brief. Um, and also, so within there, I talked about crystal structures. But if we recall, within those crystal structures, where we have close back planes and certain directions and so on and so forth. So a lot of those solid state principles we talked about as far as crystal structures and yielding and close back planes and all this. So those things mostly still apply in nanomaterials. Um, a notable change regarding surfaces, though, is that the atomic positions within a particle differ from the bulk, the volume, um, the interior, to the outside, right? That would be the surface. So in the inside, right, you have the same, especially a single crystal, you have the same relative orientation of atoms um, in any direction. And you would have many of those bonds that occur before you get to the outside. But when you get to the surface, right, now you have, at the very surface, you have atoms that can't satisfy all of their bonds because there are no atoms on the other side, right? You've reached the surface. And so you would have a situation where an atom is not as stable as it could be because it can't fully bond and form all of the bonds that it normally would. And so it doesn't take the structure that it would in the interior, having had all of those bonds satisfied. So what you get is a modification of the structure of that atomic crystalline structure at the surface. And what those atoms do is they reconstruct, they rearrange themselves to form the lowest energy conformation or configuration that they can, given the constraint that they're at the surface, right? And they're going to have these unfilled bonds. And this terminal layer, the surface relaxation extends beyond the terminal layer, right? And so there's a range under which the atomic spacing and the arrangement is slightly different, and it extends into the bulk about 5 layers. So, it takes a few atomic layers before atoms get to the point where they have their equilibrium spacing. All of the atoms have their full bonds, and so on and so forth. Right, and it's doing so to limit the number of these tangling bonds and decrease the energy of that surface as much as possible, given the constraints. And so here's a diagram where you've got here's the bulk where you've got this crystalline structure, kind of top-down view, and then you get this reconstruction where you have minimized the number of dangling bonds. And so this happens at the micro scale. It happens, there's going to be a surface layer, whatever the size of the particle is. The big thing that comes into play with nanomaterials is that your surface area to volume ratio continues to increase as your particle gets smaller, right? And so if you look at the size of the particle, right, you would have this chart here. You have the diameter of the particle on the x, and then the percentage of atoms that are considered to be surface atoms. Remember, that can extend 5 layers below the terminal layer, the very outside layer of atoms. But as you have a smaller and smaller particle, you see that the number of atoms that are surface atoms increases very rapidly. And so, here, if you have 1,000 nanometers, so a 1 micron particle, the surface atoms are essentially zero. Very few of them, relative to the number of atoms in the particle, are at the surface. But if you go down an order of magnitude, right, now you're talking maybe 4 or 5%. You go down another order of magnitude, you're talking 50%, right? You go down another, not even a full order of magnitude, and you get to the regime where like every atom is a surface atom. And so you can imagine how this fundamentally changes the properties of the material when the structure of most of the atoms is no longer the bulk crystalline structure, but this reconstructed surface. And so the energy of those atoms at the surface are higher, which leads them to be more reactive, and those particles are going to can coalesce in order to decrease the surface energy. And so you get different behavior when your particles are at the nanoscale. Different reactivities, they can behave very differently than the bulk material if you have them in these small nanoscale particles. So that's just one example. And to kind of tie back in to characterization class that many of you took last quarter, a lot of those characterization techniques that we use for the microscale are relevant to nanomaterials, right? The key thing is that we need to have resolution high enough that you can see beyond the microscale to the nanoscale. And we had some techniques that do give us information about that local environment that gets down to the nanoscale. And some of them are listed here. So X-ray diffraction, right? This is not an imaging techniques, but it does give you crystal structure information. Remember, you're looking at the constructive interference of diffracted X-rays. Now, X-rays have a small enough wavelength that you can see atomic distributions, and if you have repetition of that pattern, then you can deduce how atoms are arranged in that crystal structure. Sorry, someone just came to the door, but I guess they realized I was recording video. And so you can see how so if you go from having an arrangement of atoms, periodic arrangement like this, right, here in part A, to something like this, that's going to change the peak in the X-ray diffraction spectrum, right? So you can detect the formation of nanostructures using X-ray diffraction, even if you can't image them. You can image them, though, with technique as long as the resolution is high enough. So transmission electron microscopy makes use of very high energy electrons, right? And we talked about up here how when you have a really high energy electron, really high velocity electron, the wavelength gets very small. And so if the wavelength of that electron is small enough, it can interact with features at the surface that are of the same order of magnitude as its wavelength. And so the smaller the wavelength, the smaller the feature that you can see. High resolution TEM can see individual atoms, and so normal TEM can image at the nanoscale. Scanning electron microscopy makes use of a similar phenomena. The electrons are not accelerated to quite the same velocities, and so the resolution isn't quite as good, so you can't see individual atoms, but you can see at the nanoscale, especially in the more high resolution forms of SEM, say higher acceleration velocities, lower wavelength electrons. Scanning probe microscopies have a similar dynamic in that they can see at the atomic scale if the resolution is high enough. And so we talked about these in 680, but to quickly review, right? Scanning probe microscopy, instead of having a beam of something interacting with the surface and then you're looking at how that beam changes, scanning probe microscopy takes advantage of near field interactions. And so you've got a very sharp probe that comes into very close contact with the surface and detects some change in that probe. So with scanning tunneling microscopy, what you're looking at is a tunneling current, that you have a small current that flows through your tip into your surface, and the amount of that current is very sensitive. Depends on the local density of states of the surface, which changes as the atoms are moving. Right, so as the tip is scanned over different atoms, the tunneling current is going to change. So you can image that surface on the atomic scale, and of course, if you can do the atomic scale, then you can do the nanoscale as well. Atomic force microscopy is also a probe-based technique, as we talked about. This makes use of a tiny cantilever beam, right? That's what manufactured is essentially a small MEMS device. So you have a small cantilever beam with a sharp tip on the end, and that beam deflects when it comes in contact with the surface. And so if your tip is sharp enough, you can image at the nanoscale. This is called atomic force microscopy. So it doesn't quite get to the atomic scale under except maybe under very controlled conditions, but the nanoscale is routine, and you can do it on both conductive and non-conductive surfaces. All you need is for those atoms to the atoms of the tip and the surface to overlap and create that tip deflection in order to image the surface. And so we have a couple of imaging techniques here. These last three are more similar to the X-ray diffraction technique in the sense that you can get information about the local bonding environment, which if you have the formation of a nanostructure, like we talked about here, the local bonding environment changes. And so you can get information about that environment through Auger electron spectroscopy, so the energy, and X-ray photoelectron spectroscopy here. So both of these, the energy of electrons being emitted from the surface will change based upon the type of bond in the local electronic environment that they came from. So if I have a reconstruction in a nanostructure, I can see it in these energies of these electrons here. Same thing with the secondary ion mass spectrometry. Here, if I have a surface that starts in a different form, and when I bombard it with ions and look at the fragments, I'll get a different distribution based upon what I started with. So the point here being that it's a new field, different scale, but we can reuse a lot of the techniques and instruments that we already have as a part of our characterization toolbox. Okay, so how are nanomaterials actually made? There's two general approaches, right? You can take a top-down approach, where you start with a big object and you put a intricate pattern, a nanostructured pattern into it. Or you can start with small particles and assemble them to create a nanomaterial. The top-down approach is very similar to what we talked about in optical lithography and microfabrication. Microfabrication is a top-down approach. It's just that with nanomaterials, the resolution required is higher than for microfabrication. So it's essentially just a high-resolution microfabrication process. And you can make a nanomaterial from homogeneous or heterogeneous material. So homogeneous would just be it's the same material, so you're putting a pattern in a material, but not, say, depositing one material in another material. And so here, you're going to be interested in facilitating island growth over step propagation. So remember we talked about in epitaxy how films grow, where you have the atoms hitting the surface, diffusing, finding that step, and contributing to the growth of that atomic plane. And if you have atoms arriving too quickly, then they don't have time to find that plane, and you get island growth. Well, for the sake of growing a nanomaterial, you may want to actually encourage island growth and then find some way of creating these islands in a pattern. Heterogeneous, we're talking about different materials. So you're going to have, just like we talked about with CVD and epitaxy, when you have two different materials, there's a lattice mismatch and surface energy at that interface, which can produce strain in the material and can lead to some reconstruction there at the interface. How you model that interaction, especially at the nanoscale, depends upon what this lattice mismatch is and what the relative surface energies are at that interface. So it can be a more complex problem. Since the top-down approach is an extension of microfabrication, right? We're gonna use the same techniques we use in microfabrication, And the big difference here is the resolution that we have in our photolithography process. But depositing metal, depositing semiconductors and insulator, we're going to use PVD and CVD just like we did before. But since we're going, at a much smaller scale, additional techniques have been developed to facilitate that. One of which is nano imprint lithography. So if you think back to what we talked about in lithography, where we had non-optical, where we're talking about X-ray based or extreme UV or electron beam. So you can use an electron beam to make really small features, right? Say nanoscale features. The problem is that it's a direct write process, and you can make one, but it's very time and resource intensive to make that one, as opposed to microfabrication, where once you make a mask, you can replicate it 10,000 times. And so that same idea is trying to be recycled, in the sense that, okay, I have the techniques to make a really high, really detailed mold, essentially, or a mask. And in nano imprint lithography, what you're doing is you're using that mask that you've made, that highly patterned mask, and instead of using it as a mask, which is limited by the diffraction of the light. So if we don't have those really low wavelength sources, having a really detailed mask isn't going to help us, right? Because the light is going to diffract through those really small spaces, but you can use it as an imprint mold. So nano imprint lithography, instead of having a mask that light shines through, you have, say, deposited resin that is patterned by the mold. So you have contact between the mold and the resin. The resin fills the spaces in the mold, and the mold is transparent to ultraviolet light. So you have ultraviolet light shining through the mold and hardening all the photoresist, but it's been molded into different thicknesses in different regions by that mask or by that mold. And then when you, after it cures, you can release the mask, and now you have a pattern of photoresist that matches the shape of the mask, right? So you can reproduce that pattern, not through changing chemically with UV light certain regions by having an opaque and transmissive regions on the mask, but here you have different thicknesses. So if you come in later with an anisotropic etch, say like an ion etch or something, right, you're going to etch away the thin parts of the photoresist before you etch away the thick parts, and that allows you to reproduce this pattern. So nano imprint lithography is nice because you can reuse the mold, and can be higher throughput than, say, serial writing, because you can imprint, expose, and then go on and make another one. Whereas in serial writing, you might have a scanning probe or an electron beam that allows you to make a highly detailed mold, but you make it once, right? And then you got to start over and scan and print another one. So nano imprint lithography. So that's the top-down approach. The bottom-up approach is has potential to become more economical, because you don't have to go through all of the expense of making a mold or a mask and then using it. The bottom-up approach, if you can get the chemistry right, the nanoparticles make themselves. The trick is to get that chemistry right so that they arrange spontaneously the way you want them to, right? And you can imagine the molecules aren't really interested in cooperating with us, so this is complicated. You can do it a number of different ways. For simple particles and simple arrangements, you can kind of have this have like a co-precipitation route where you're essentially kind of stacking the deck for it to form in certain ways. So sol gels are a network of silica particles. And so you can form these particles, and then depending upon the treatment that you put them under, whether, let's see if I can zoom in on this particle here, this little diagram. Depending on how you precipitate them, or how you could spin them or coat them or have them gel up, you can take these sol gel particles and arrange them in films or in gels or in fibers, and the chemistry of that arrangement process can form nanoscaled features, right? Not as well patterned as some other techniques. And these co-precipitations are kind of like what I would think of as being kind of loosely nano fabricated, and you get less repeatable results, but the features are on the nanoscale. Next, you'd have micro emulsions. So an emulsion, even from cooking or something, is a mixture of oil and water. The difference between just a regular emulsion and a micro emulsion is that the particles, right, of oil and water, and and the interface between those oil and water is a surfactant. So surfactant is a molecule that has polar and nonpolar regions, so it kind of bridges the gap between oil and water. Because you'd say, well, oil and water don't mix. Well, they do if you have a surfactant, because you can make a really small particle of oil that is stable in the water because the surfactant is at the interface. Anyway, if you can make the particles small enough, right, then they'll be on the nanoscale, so you can have this microemulsion. You can also make use of hydrothermal synthesis to make nanoparticles. We talked about hydrothermal growth in our crystal growth discussion, and that, if you recall, made use of different solubilities in solution at different temperatures. And our hydrothermal growth reactor beforehand had basically a cold and a hot end. At the cold end, you had seed crystals, and at the hot end, you had your feedstock. So at the hot end, it would dissolve the feedstock, and then it would come out of solution at the cold end and form of a growing crystal. Depending upon the growth conditions, right, you can get nanoparticles if you encourage a high degree of nucleation instead of encouraging a low degree of nucleation and the growing on the seed crystal. And then lastly, you have organic semiconductors, which form nanostructured elements, because these are relatively large molecules that self-assemble. So this kind of starts to get close to what we talked about here in the second way, this self-assembly. So rather than focusing on just making really small particles on the nanoscale and then they kind of arrange themselves loosely based upon our external inputs, self-assembly is using chemistry and building the molecule or the particle such that it has a tendency to arrange itself how we want it to be arranged, right? So, for instance, you could build a molecule that has hydrogen bonds in certain parts of the molecule, or in certain, or forms particles where those hydrogen bonds go into certain regions that encourage them to bond in a reproducible, orderly fashion, right? The same thing with electrostatic, where maybe you have a molecule that has an ion complex, or something that you can use an electrostatic field to say make nanorods align or something like that. The shape of the particle, right, can be like a puzzle piece, so they fit together just one way, right? That can lead them to self-assemble. You can make use of hydrophobic, so water-fearing, or hydrophilic, water-loving regions, and this kind of gets into this same idea we talked about with a surfactant, where you can use those properties to get them to align with one another or form groups, right? And then also there's template-assisted self-assembly where you can, where you have a template. So by other means, you've made regions where particles will fit, and then you can use that to create an orderly arrangement that that gives you structure at the nanoscale. Okay, so we've talked about the background of nanomaterials and ways of characterizing them and how we make them. So what are some of the potential applications? Well, here I have a couple. I have essentially electronic, bio applications, and then mechanical applications. So we'll kind of try to go through this a little bit more quickly so I can keep this in a reasonable video length. So starting with the electronic materials, the question I guess becomes, in the microfabrication we were driving the size of the device smaller and smaller and smaller, so we could pack more of them in the same area, and they can run faster. So at what point does that process exhaust itself? Essentially, what's the limit to how small you can make a transistor? Well, I would say that I guess you could reduce the size until you're talking about manipulating individual electrons, right? So an electronic material, the quantum of electricity would be a single electron. And so you get into talking about single electron transistors based on quantum dots or tunnel junctions. This produces some interesting kind of quantum mechanical changes in the sense that it's very similar to what we talked about with the surface area to volume ratio, in that there's this idea called a Coulomb blockade, where that is the increase in charging energy caused by adding one more electron. And so you can see here, it's essentially sorry, my phone is going off. My wife is walking around. It's very distracting. And so there's an energy cost to adding an electron into a transistor, right? That's the Coulomb blockade, because you've got electrons in there already, and you're trying to add an additional electron. And so the Coulombic force between electrons that are there and the additional electron gives you this Coulombic repulsion. And so similarly to what we saw with the surface area to volume ratio, as the quantum dot, right, or some region of semiconductor material that forms our transistor, when it's very large, right, the energy that is required to add an additional electron is very small because there are already so many in there. Right? I mean, we see it's divided by r, so we have this linear relationship between this excessive energy and the radius. And so, like we saw before, as the size of that transistor region gets smaller, the excessive energy is increasing. And so we see, not only do we see that it becomes harder to add that single electron, but the net charge in that quantum dot becomes discrete, right? Because we're adding, we can consider adding one electron at a time. So, the charge in the device will jump discontinuously every time that I add an electron, which is a departure from sort of the continuous charge or voltage within the device as a function of the current that happens with a larger device. We also see quantum effects at the nanoscale with regards to the energy band structure and the resultant optical properties. If you recall earlier, I talked about the electron in an infinite potential well, and how in that well it created discrete energy levels. If you take a semiconductor material and sandwich it between a different semiconductor material, if the material inside the sandwich has a smaller band gap than the outside, it forms a potential well. Inside that potential well, you have these discrete energy levels. And so if you make a semiconductor device that has these layers that are on the nanoscale, then this quantum nature asserts itself, and you can make transitions between these bound states in the valence band and the conduction band, which allows you to control the output, the optical output of your device. So if I can control very precisely the thickness of this semiconductor layer, then I can have control over the energy spacing of these bound states and also the transitions between them, right? The energy of the transition is dependent upon where those bound states are. So if I can control this thickness, then I can make a device that emits a wavelength at any wavelength that I want. And so that's why it's so important. We talked about molecular beam epitaxy having the ability to deposit one layer of material at a time. That if I want to have that tight control over the thickness of this layer, right, I may need to deposit, a certain number of atomic layers in order to achieve that. And at thicknesses here where we are, right, so we're approaching the de Broglie wavelength of the electrons, which is what drives this quantization of these energy levels, similar to the quantum well, as I said. And similarly to that, these quantum dots, so if I can, this is like sort of a quantum well, so this would be like kind of a one-dimensional nanostructured material. And that would be as opposed to a quantum wire, which would be a two-dimensional, right? So I would have nanometer scales in 2 dimensions, or I could have a quantum dot, which is where I would have essentially a dot, which is constrained in all 3 dimensions at the nanoscale. And so that's similar to, say, having a certain size nanoparticle, say, in solution. And what happens also is that if you have a quantum dot, as the size gets small, right, we have a rapid change in its optical properties. And so I think this is for maybe gold nanoparticles, where you kind of get maybe a reddish, yellowish, but as the particle gets smaller, right, I get this rapid transition through the visible, where the color of the solution is very dependent upon the size of that quantum dot. Or we could think of it also as, the thickness of this quantum well. Okay, on the bio-nanomaterials. So there are nanometer structured materials that just exist, that are not man-made. DNA is probably the ultimate self-assembled structure, right? It's constantly replicating and refolding and very dynamic. And so there have been many researchers who have tried to use that natural self-assembly of DNA molecules, right, and our increasing ability to manipulate DNA, to use it as essentially kind of like DNA Legos to build nanomaterials. So you get a DNA molecule and you functionalize it with sticky ends, and it forms, it bonds in a way that creates this nanostructured material, which then you can use as scaffolding to deposit other materials and get them in the right positions and to make structured arrays. There are naturally occurring nanostructures. A great example is gecko feet. So geckos can, walk upside down on very smooth surfaces because their feet have um, ridiculous numbers of little hairs, right, that are, um, you know, um shorter than, our hairs are thick, and they have this little, spatula at the end, and so these really tiny hairs give their feet like super high surface area and really small size, so they can basically follow the micro roughness of whatever surface they're on, um, and that gives them, a much better grip. And so efforts have been made to replicate this structure with artificial materials. And so if they can micro pattern these similar structures to what you find on gecko feet onto polypropylene films, right? Getting the fibers on the surface to have the right length and to have um, the right flexibility is key to have it follow that micro roughness profile. But as you can see in this picture here, right, they have this 2 centimeter square patch that's holding up 400 grams on by sticking to glass. So it can work. You can also take advantage of the sensitivity of nanostructured materials um, to make easy diagnostics. So if you have a nanoparticle-based biological detection, right, you can kind of make use of this natural chemistry and also the optical properties change that we talked about. And if you have a modified nanoparticle, say that has a certain molecule on the outside of it, when it is in the presence of another molecule to which it bonds too strongly, um, you can take dispersed nanoparticles and have them cluster, right, at certain temperatures, or they can cluster and change the optical properties, which gives you, I guess maybe it might even be linked, where they cluster at a certain temperature, which gives you the optical properties. At any rate, the presence of a certain biological marker can produce this easily identifiable change, and that's the basis of a very simple diagnostic tool. And so you can detect, right, gases or small molecules or proteins, and so on and so forth, right, just with sort of the details of how you build these nanostructured molecules. Okay. Last topic is the mechanical properties of nanostructured materials. As we talked about in the first half of this course, I feel like over and over again we saw this trade-off between strength and ductility, which is key to toughness. So as a material got stronger, it would become more brittle, less fracture resistant. There's always this trade-off, this inverse relationship. However, if you can reduce the grain size, then you basically get both. We saw this relationship here between yield strength and grain size. This is pretty common. This is the Hall-Petch equation. And we talked about this in the context of cold work and recrystallization, in the sense that you can get stronger material if you can reduce the grain size. We did that through, again, cold work and recrystallization. And the more you deform the material, the finer the grain size you could get after you allowed it to recrystallize. And so if you can just do that to a very large degree, right, you could get crystals on the order of nanoscale, right, which gets you a nanostructured mechanical material. This equation here is not from Callister, because in Callister, when we talked about fracture strength, we were talking about flaw size, right? We didn't look at the impact of grain size on the fracture strength, but it turns out that there's the same relationship here on fracture strength with grain size as we saw in the Hall-Petch equation. So if you can reduce the grain size, you actually get both. Material strength increases and toughness increases. And so we see that with recrystallization. You can also get it through certain ways of forming martensite. So if you can quench to form what's called lath martensitic steel, and that's where you get uh, regions of the crystal of the austenite grain. So remember, we're quenching from a solid, austenite, and so that is going to have grains. And when we transform to martensite, right, we don't really get grains. We get these needle-like growth patterns that are very finely structured and very hard for dislocations to move through, which is where we get the strength for martensite. But if it grows not not in these needle grains exclusively, but actually forms smaller regions that act as grains within the austenite grains, which they call lath, then the size of the lath can be the grain size in these equations, and so you can reduce the size of the functional grain, which allows you to get down to the nanoscale and get yield strength and fracture toughness. Measuring the mechanical properties on the nanoscale is trickier. If you do a tensile test, then you're going to be measuring macroscopic properties, where you're going to need a piece that's big enough that you can grab it with your grips and pull it apart. And so you're going to be looking over a scale that's much larger than the nanoscale. When we talked about microscale mechanical measurements, we were looking at hardness testing, where you'd have a Vickers or a Bernal hardness, say a small diamond probe or a small ball-shaped probe, where you're pressing in material and measuring the size and shape of that indentation. Well, you can do that at the nanoscale. The problem is you need a smaller indenter. Well, you can make a smaller indenter. With the AFM, there are techniques to measure mechanical properties, and they allow you to make a lot of the same measurements that you would make in traditional hardness testing with the AFM. The last thing I'll mention here with regards to mechanical stability is that one of the easiest ways of making a material with a dimension on the nanoscale is to just have a really thin film. The problem is that when you reduce thin films to the nanoscale, you get a different distribution, or different manifestation of induced stress. So if you, as a function of forming this film, right, you have induced stresses due to the way it was cooled or its proximity to a certain particle, then this thin film is going to, that stress gradient is going to increase the energy of that film, and so it's going to look for a way of relaxing that stress. Oftentimes that is through buckling. So you'll find that it forms this wrinkle pattern that can be somewhat random or correspond to whatever's causing that stress gradient, which can be a real problem if you don't want it to, if you wanted to have a flat thin film. But you can actually make use of this because of the periodic nature of this buckling. When I was doing my master's work with the AFM, the guy that I was working with did a lot of research on seeing if there was a way of tuning the AFM to create this buckling in a reproducible, controllable way to essentially make a nanostructured material using the buckling. At any rate, so that's all I have. Hopefully that was an introduction that kind of helped to put nanoparticles, nanomaterials in context, give a little bit of the background of this emerging field. So this will be the last video of the quarter. Looks like I went over a little bit, but this is essentially a 2-for-1. Last year I covered nanomaterials in 2 days. So Friday we'll do a Q&A, and that will be all. There should be course critique forthcoming. I have not seen it in my email yet. They were trying to add sections related specifically to the DL format to try to improve things for next quarter. I won't be here next quarter. A couple of weeks from now, maybe a month or so, I'm going to be packing up and going to Albuquerque. So thanks for a couple of great quarters. I wish you guys the best in your research. I hope that things can get back to normal, especially if you have experimental theses, that you guys can get back in the lab and get back on track with your program and get out there and start doing great things for our Air Force and for our country. Anyway, thanks.